scores for 12 randomly selected students, first and second time they took the SAT. At our level of significance there, is there enough evidence to conclude that the SAT scores changed? All right, so there's no indication that they improved or they got worse, but just that they changed. Assume the populations are normally distributed. All right, so what we're going to do here is take the difference and we're going to do a t-test on the differences. The null hypothesis for this test is that the mean of the differences is 0. And the alternative is that the mean of the differences is not 0. In this case, because it just said change. It didn't indicate that they were higher or they were lower, just said that the claim was that they changed. All right. So if they change, that means this is either a significant positive difference or a significant negative difference. So changing would mean that the mean of the differences was not equal to 0. And we'll define it, the mean of the differences. Between the first and the second taking of the SAT. All right, so we've got our hypotheses. We have our variable defined. Step 2 is level of significance. There it is. And so on this particular test, it is two-tailed again. And in this case, alpha. So we're going to, if we do the classical approach, so you wanted to see some graphs, two-tailed test. And this is not different from what we did in that previous problem. Except now this is a t-distribution. So even though this is alpha over 2, which is 0.025, just like we had in the previous problem, we're now dealing in a different distribution. And the distribution is a t-distribution. And the degrees of freedom is 1 less than the sample size. And since our sample size is 12, the degrees of freedom is 11. So to determine these critical values, we have to go and find the t critical values. So these could be the critical values from 10.3, where we use a t-distribution, 11.2, where we use a t-distribution. And today you're going to see that section 11.3 also uses the t-distribution. All right, so the left area is 0.025, the right area is 0.025, and this table gives us the right area, 0.025. Right here, notice we've got 95 right above it. We're doing a confidence interval. And then you go down to degrees of freedom 11. So there's 2.201. So this one is 2.201, and this is negative 2.201. The variable that we would use for these critical values, similar to what we used before, but instead of the z of alpha over 2, we're going to be using t of alpha over 2. These are the critical values. There are 2. You always have 2 critical values in a two-tailed test. In a one-tailed test, you have only 1 critical value. Do not reject. And then we have 2 reject regions. And the only thing we can reject is the null hypothesis. If you didn't have the table, and so if we were dealing in a z distribution, we would use inverse norm. But since we're dealing in a t distribution, we have to use inverse t. All right, and so if we give the left area here, it's 95 and then 2.5, that's 97.5. And then the last number is the degrees of freedom, so 11. So left area for this function and degrees of freedom. Over here, inverse t, now the left area is just 0.025. But again, the degrees of freedom is 11. So let me just show that. Inverse t, number 4. If you don't have this on your calculator, it's in one of the programs. So 0.025, and this would be the area if you have the menu, and then degrees of freedom comes next. And if you do the 975, notice you'll get the same exact number, but the positive version. And if you round this to 3 decimal places, you get 2.201. And that's exactly what we found from the table. So you can actually check your critical values if you want in this t distribution. All right, so now we're ready to calculate the differences. And if you want, you could do this in your head, or you could do it one at a time so that we don't make mistakes. I'm going to go ahead and just type in the score on the first test will be L1, the score on the second test will be L2, and then the differences I'm going to put in L3. So I'm going to clear out list 1, list 2, list 3. All right, so this will take me a couple of minutes to get these typed in. All right, it's always a good idea just to kind of scroll down to make sure you don't have any obvious input errors, because one little change of a number can dramatically throw off your results. Now, once you have those in, highlight L3, and here's where we're going to calculate the differences. So I usually just take L2 and subtract L1. And that'll subtract all of these numbers, and then I'll enter them in here. All right, this first student had an increase of 75 points, very good. And the next student had an increase of 104 points, also very good. So you can see that from maybe the first time they took it was when they were a sophomore, and the second time they took it, maybe they were a junior, and there's every single student had a, looks like a fairly big increase in their score. So it shouldn't be of surprise to you when you see that our null hypothesis is going to be rejected here. All right, so the differences, L1, L2, L3 is equal to L2 minus L1. All right, now we're going to do the t-test, and the mu0 value is going to equal 0. It's this number up here, mu0. The input, since we have the differences, the raw data in list L3, I'm going to select the data option, refer them to the list. The frequency will be 1. And then that would give us the mean, the standard deviation, and the sample size that we know is 12. All right, and then mu not equal to mu0. All right, I'm going to plug all that in to the t-test, stat, tests, and then option number 2 is the t-test. I'm going to select the data option. mu0 is 0. My list is L3, frequency of 1, not equal to in the alternative hypothesis. Calculate. All right, so you can see here, yeah, we knew it was going to be a statistically significant. This is 9 standard deviations above the mean, right? So this is very unlikely to occur if there wasn't actually an improvement in the test scores. So our test statistic is 9.016, and please don't write that the p-value is 2.06, because the p-value is not 2.06, even though that's what it looks like here. You got to read that from left to right. So that's times 10 to the negative 6. So you have to move that decimal point 6 places off to the left. I'll call it that. So 2.05937 E negative 6. All right. If you think it's 2.05, 2.05 is going to be larger than any alpha, so you're going to fail to reject the null hypothesis. And if you did that, then you'd get the exact opposite decision that you want. All right, it's important to write down these summary statistics here. And so X bar, which is actually our D bar, it's the sample mean of the differences, it's 68.5. This means that on average, those taking the SAT twice improved on average 68.5 points. Very good. And then the sample standard deviation is this, and the sample size is 12. All right, so we have P is 0.000002, and we have alpha is 0.05, and P is clearly less than alpha. To see this, all right, so we reject the null hypothesis. If you instead took this test statistic and labeled it somewhere on this graph, here's 0, here's our critical value, but 9 would be way over here. So you can see that this reject region extends way over here. So that number is way off to the right, but it's going to fall in the reject region, so that the same decision would have been made. And then step 5, right, we are going to reject the null hypothesis. So we are going to reject it in favor of the claim that says that there clearly is a difference between the first and second taking of the SAT test score. So we'll just write that up in layman's terms here. There is evidence to, all right, reject the null hypothesis, which means show support for the alternative hypothesis, which also means to show support for the claim. And I'll just say something like, on average, students performed better on the second taking of the SAT test. All right, so a lot of times when we do a two-tailed test, we also calculate the 95% or calculate a confidence interval. And so we're going to be using the 2-prop. Nope, not this time. We're going to be using t-interval to correspond to the t-test. So stat, tests, t-interval is down option number 8, I believe. Again, we're going to select data because we have all of our differences in L3. So data L3, 1. We are going to change the confidence level to 0.95 to correspond to an alpha of 0.05. And then what do we see? Huge positive numbers. So 51.778 and 85.222. Now we said that, maybe we were just going to look at whether those two numbers were positive or negative. You can see they're positive, but they're, hugely positive, right? So this last worksheet that we did, if you see positive, positive, that means the mean of the differences is positive, which means in this case, there definitely was an improvement in the SAT score, second time they took it, and that gives support for the alternative. And we definitely rejected the null hypothesis to show support for the alternative. This one we can actually interpret, maybe I should go back to what was entered in there. So the input was data, and list was L3, and frequency was 1, and C level 0.95. Now this one we can say something like this, and I might as well interpret this one using that kind of template language that I gave you. We are 95% confident that the average SAT improvement is between 51.8 and 85.2 points. All right, so here we are actually using these numbers to interpret this confidence interval. One question: what did the 9 have to do with the reason we reject the claim? Okay, I think Kendall's referring to this 9 here. So this is called the test statistic. And it's a t-value, just like our critical values are t-values. So when we plot the t-values, whether they be the critical value or the test statistic, they have to be plotted on the t-axis. So this is a t-distribution, so this is the t random variable. And here, this is actually t0, what we assume to be true. And so we have this kind of line in the sand, and everything beyond this or over here would represent the most extreme 5% of all the samples. And so if we get a test statistic way out here, 1, 2, 3, 4, 5, 6, 7, 8, 9, it would fall way over here. It's way in the reject region. So this 9, what it does is it enables us to say we reject the null hypothesis. So it's an alternative to make the decision to the p-value approach. In practice, we really only have to do one. And since our technology will calculate the p-value quickly, most of the time we use the p-value. But this is a nice way of linking it back to all that work we did in chapter 7 and in chapter 8. So since 9 is way out here, it's in the reject region. What do we reject? We reject the null hypothesis. The frequency is, for the calculator, is always going to be 1 when we enter it in like this. And the way that you think about it is this. The reason the frequency is 1 is because our sample size is 12. We only have 12 students here. And we only have one student that had both of these two scores. So these two scores together had a frequency of 1 because just one student had those 2 scores. And one student had these 2 scores, and one student had these 2 scores. So the frequency of each pair of scores was 1. We rarely use that frequency number to be something other than 1.